Hello, thanks for watching. In this video, I'm going to derive the Laplace transform of sine. I'm going to split it into two sections, one where I perform the derivation, and then a second half where I evaluate an integral using the Laplace transform of sine. So I'm going to use the simplest method to derive this, for the reason that I don't want to assume any properties of the Laplace transform while deriving it. I'm going to go straight from definition, so the definition being that the Laplace transform of a function is equal to the integral from 0 to infinity of e to the minus st times the function itself. So if we have the Laplace transform of sine, we have the integral of 0 to infinity of e to the minus st multiplied by sine of at dt. So the simplest method is going by parts. So if we remind ourselves of this formula, then we have, if we set u equals to sine of at and v equal to, oh, not v, sorry, and v dash or prime equal to e to the minus st, we get that v is equal to minus 1 over s of e to the minus st, and we get that u prime is equal to a cos of at. So using this, we get that minus 1 over s e to the minus st sine of at from 0 to infinity plus a over s with the integral from 0 to infinity of e to the minus s t times cosine of at dt. So if we want to evaluate this, we evaluate its limit as t tends to infinity and as t tends to 0. Well, when t tends to infinity, we don't know what this is. This diverges. However, we know that it would have taken a value between minus 1 and 1, whereas this goes to 0. So when this whole thing approaches infinity, we get 0, and then when it approaches 0, we get that sine of at also approaches 0, whereas this approaches a finite value. Hence we may conclude that this whole thing is just 0 plus 1 over as of the, not 1 over as, a over s, sorry, of this function. Now we repeat the process from before, and we set u equal to cosine of at, and therefore we get that, and also equals to e to the minus st equals to and therefore when we put this together, we get that the Laplace transform of sine of at is equal to a over s of, well, we multiply those together, and so we get minus 1 over s e to the minus st times cosine at from 0 to infinity minus this integral here, also a over s on the front. However, we should notice that this is just the Laplace transform of sine from the very start, so we'll mark this down as Laplace transform sine of at. Okay, so now we want to see what this is by the same logic as before. When it approaches infinity, when t approaches infinity, this function approaches 0, but this time when t approaches 0, we get we don't have a sign, so actually cos of at just approaches 1, and e to the minus st also approaches 1, so we have 0 minus 1 over s, sorry, we have 0 minus equals 1 over s, so actually we have Laplace transform sine equals a over s 1 over s minus a over s, the Laplace transform of sine of at. So now we just need to rearrange for the Laplace transform of sine. So we get that the Laplace transform of sine of at is equal to a over s squared minus a squared over s squared sine of at, and therefore the Laplace transform of sine of at equals a over s squared over 1 plus a squared over s squared, which is just equal to a over s squared plus a squared. So that's our Laplace transform of sine. And now we're going to think about how we can apply it to a problem. So I'll give an integral which doesn't have an elementary antiderivative, meaning that if we had no limits, then we wouldn't be able to find some nice function that we can just plug in limits for and find the value. So if we have this, now this gives a really nice answer, but we don't use the usual strategies we use for an indefinite integral. So the first thing we should notice is that this is just simply the Laplace transform of sine x over x. So now I am going to use a property of the Laplace transform, which will be derived in another video. So if we have the Laplace transform of some function over t, then this is just equal to the Laplace transform of the integral from s to infinity of the Laplace transform of the function itself. So what we want to do here is notice that this is equivalent to and so what we can gather from this is that this is equal to 1 over, and see, we derived that the Laplace transform of sine is just, it's this. Therefore, when we plug it in here, we have a simple integral, because we know that this just evaluates to arctan of sigma. And now if we have our bounds, this is equal to pi over 2 minus arctan of s. Okay, so what is s? In our case here, we were just missing an s here, so if we had this, we would have an s, but in our case, this s is just 1. So this is equal to pi over 2 minus arctan of 1, which is just pi over 2 minus pi over 4, which is equal to pi over 4. And so when we have this integral, it evaluates to pi over 4, which gives a really nice result for an integral which does not have an elementary antiderivative. That is the end of the video. Thank you for watching.